Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. This is Adib, your lecturer for Microsoft Materials. So this recording is mainly for chapter 7, Transverse Shear. But before we go to chapter 7, let's look back at this stuff, FLEXURAL formula, before we go to chapter 7. Okay, remember from last chapter, chapter 6, about bending, we learned in 6.4 about FLEXURAL formula, right? And then in FLEXURAL formula, we have derived these two. Actually, they are the same. These are called FLEXURAL formula, this one and this one. Actually, the main formula is this: sigma is the bending stress equals to minus m, internal bending moment m. Y here is the distance from neutral axis to the point that you want to find the corresponding stress here, and then over I is the moment of inertia of the cross section, right? So m and I for the section will be constant. The only variable here is the y, the location. So as you can see, if the y is 0, for instance, here you have this neutral axis. For instance, you have this neutral axis, right? And then you have the top portion. You have the top portion, you have the bottom portion. So at y equals to 0 at on the neutral axis, then your bending stress will be 0, and it will increase linearly until it reach the maximum. See, it increase here 0, increase linearly until it reach maximum at the top surface, or increase until reach maximum at the bottom surface. So which one is bigger? It depends. I mean, how actually the neutral axis is oriented, right? So which y is bigger here between these two, right? And remember that actually, because the m, if the m is this way, so the bottom part will be in tension, the top part will be in compression, right? So again, sigma max y equal to y it is mc over I, because y you can substitute y to become c. So the c is actually the furthest distance, right? Okay, this is for bending stress due to internal bending moment m, right? So up to chapter 6, we have learned in chapter 4 about this formula, sigma equals to P over A, which means that if you have the internal axial load P, and then you just divide with the area, and then you get this internal this is normal stress due to the internal load P, right? Internal normal load P. And in chapter 5, we have this we learn about the shear stress due to internal torsional moment T, right? And then we just focus it. I think the chapter just focus on the circular cross section, and that's the reason for that. Otherwise, we will go into too much details on, different types of sections. But the general idea is tau equals to T rho over J, and look at that. What is rho? What is J? J is basically polar moment of inertia, while rho is actually, again, is like C, like not C, Y in chapter 6. It is rho is distance from the center of the circle, right? So rho is 0 here, and then it becomes maximum at C, right? And in chapter 6, like we just discussed, chapter 6, I'm not sure what happened to the marker. In chapter 6, so we learn about the internal bending we learn about sigma, which is bending stress, normal bending stress, equals to m minus m y over I. M is the bending moment, m, and y is the distance from neutral axis, right? And then divided by the moment of inertia. Let me change the pointer. I'm not sure what happened. Okay, just forget about that. Okay, next we will go to chapter 7, which is transverse shear. So okay, before that, you realize that actually if you have previously, if you have this P highlighter, if you have this P, right, and then you will have the normal stress. If you have internal torsional moment T, will give you the shear stress. If you have bending moment M, then you will have normal stress, right? So realize that this is normal stress, and this is normal stress as well, and this is shear stress. So you have to map them. If you have internal normal load P, will give you normal stress. If you have the internal bending moment M, you will have normal stress. If you have internal torsional moment T, you will generate shear stress. Right? So in chapter 7, transverse shear, as the name implies, shear. So you will have the what type of shear? Normal or shear? What type of stress? Normal or shear? So it is a shear stress, right? Okay. There are only two subtopics, 7.1 and 7.2, that we will cover. And so the first one is shear in straight members. So we're going to discuss on a little bit on the theory first. The transverse shear stress always has its associated longitudinal shear stress acting along longitudinal planes of the beam. So basically, if this is the beam, let me change again. So if this is a beam, and then you apply a transverse load V, right? Like shear load V, and then we'll have this tau, right? And it varies. That's very simple to understand. The sentence here actually it explains about if you take one particular element here, take it out like this. You take one particular element out. This element, you take it out, and then what happened here is this is the tau. Okay, this is the tau from the diagram, from the surface, right? This tau. So if you have this transverse shear stress, we call as transverse shear stress, what you will have as well is this longitudinal shear stress. What is meant by that is this is longitudinal direction, okay, or the other way around. I mean, doesn't matter. This is longitudinal, so that's why we call this as the longitudinal shear stress, and this is the transverse direction. Okay, if you have the transverse shear stress, you will have longitudinal shear stress. This is important. Probably, I mean, looks like playing around, but actually this is important because we need this understanding to derive the transverse the shear formula later. Okay, so this is what called as a complementary property of shear. Just a quick recap. If you remember, in chapter 1, when you draw about the not chapter 1, chapter 3, when you draw the shear, the normal or shear stresses, something like this, normal stress like this, and then you have the shear stress. You remember that if you draw shear stress, you have the complementary. If you have one like this, and then you need to have the complementary, otherwise they're not in equilibrium. Okay, otherwise it won't be in equilibrium. So you need to go back to this and check back on this complementary property of shear. So this understanding of complementary property of shear will explain why you have the longitudinal shear stress when you have the transverse shear stress, right? Okay, so we'll look at the effect of shear stress. This is physical effect. I mean, you can try it on your own. If you have 3 boards, and you do not bound them together, and then you apply the load, right? You make like a simply supported beam or whatever, and then you apply the load P on the top. You do not bound them together. What will happen is that they will slide between them, right? You can see that they slide between them when the beam deflects. Okay. On the other hand, if you bond them together, for instance, you use glue or whatever, you can try to use nail or whatever, but you bond them together, you apply the transverse load P, right? What will happen is that now the glue, for instance, it will prevent the relative sliding between the boards, right? And consequently, this beam, the three boards will act like a single unit of beam. Okay, so this is the effect of shear stress. So actually now in this example, what really happened is now you shear stress is developed between them. Okay, and we'll discuss a bit on warping of cross section. What happened here is, okay, this is a short beam. Okay, short beam. Before deformation, if you draw horizontal and vertical lines, you will have these very nice cubes. Kind of cubes, right? And then once you apply the V, the transverse shear load V, what will happen is that you will see the warping. So what will happen is that it will have this these lines, the horizontal and vertical grid lines, will deform and it will wrap like that. See? Okay. Why this is important? Why this discussion is important? This is important because if you remember, and you should remember, that we assume that after the load is applied, plane section remains plane. When we want to use flexure formula in chapter 5, and when we want to use torsion formula in chapter 6. When we use flexure formula in chapter 6 for bending, and when we want to use torsion formula in this chapter 7. Okay. So this actually violates. This warping will violate because you can see that actually the plane section now, it doesn't remain planar anymore. Okay, but rest assured, we can use the formula. We're going to learn. The reason is because in most of the problems, actually we will consider slender beam. Okay, so warping effect is negligible in slender beam. So this is what we call as a short beam, short, S-H-O-R-T, short beam, or stocky. Just a fancy name given. Short or stocky beam. What does it mean by that is that if the beam has very long length, okay, compared to the thickness, so they call it as a slender beam. If the length is short, and then it is quite thick, so we call it as a short or stocky beam. So this short or stocky beam is problematic to be analyzed by using flexure or torsion formula. Okay. Okay, now we go to the shear formula. For the shear formula, actually this shear formula is not developed directly by using shear. In the derivation, actually the one which was used was the one by the M, you see, internal bending moment, like the one in chapter 6, right? So I'm not going to go into the details. If you are interested to know the details, you can ask me again, but otherwise I'll just tell you what really happened, in summary. So what happened is that you make a section here, and then you take the section. This is the section, right? when you apply the distributed load and the whatever distributed loads that you want to apply, even couple moments, then you draw the free body diagram. You will have this kind of variation. You see, you have the internal moment m here at this side and a direction of m plus dm at the other side. Okay, so the section is like this. If you draw the neutral axis, you have the neutral axis somewhere here, and then if you want to analyze this line, I mean the points on this line, so basically you find it as to be y bar distance from neutral axis, and then the remaining area a prime, the area of a prime will have its centroid will be y bar prime from neutral axis. Okay, so what happened is that now we want to derive the shear formula. Okay, so what happened is that we cut here, like I said, we cut, and then we take we look from this side, and then this is the view, and then like I said, because you have m here and we have m plus dm at the side, so you have this kind of free body diagram. And then once you did all of that, you will need this complementary this complementary tau shear at the surface at the bottom here, right? So if you look at the view, so you have this tau, okay, to be the equilibrium, because one side is m, another side is m plus dm. So what happens that you need this tau. So actually this is the tau, this is longitudinal tau. So once we have this longitudinal tau, then we can have the due to the complementary property of shear, you will have the transverse tau as well. Okay, so if you do the force equilibrium in x direction, in the longitudinal direction, you will end up like this, and then you simplify them, and then it will become this tau equals to 1 over I t dm over dx integration a prime y d a prime. Okay, and then you realize that actually this dm over dx is actually this. Remember from chapter 6 when we talk about 6.2, the graphical method, we discuss about the slope of internal bending diagram, internal bending moment diagram, dm over the dx is actually the shear force itself, right? So this is v, and then this integration y dA prime is actually Q. I mean, we name it as Q, moment of inertia about neutral axis. Moment of area, not moment of inertia. Moment of area about neutral axis, and then you can simplify to become y bar prime a prime. Okay, so we look at this. What are these? What are all these? Okay. So the formula, the shear formula is tau equals to VQ over IT. QV, again, V is simple. V is your transverse shear force, right? I is the same like the one in chapter 6 in bending. It is moment of inertia. Moment of inertia about neutral axis. So it will be the same for each section, right? And what is Q? What is T? So T, okay, we go back to this figure. This is neutral axis, right? And then if you want to find shear stress at this point, for instance, what you have to do is that you have to draw a line which is parallel with neutral axis. Okay, this is the thickness T. T is the thickness. So this T is this thickness, right? And what is Q? Q is this. You see the remaining portion area. Okay, this area A prime. Okay, so the centroid here, the distance from the centroid to the neutral axis, we call it as y bar prime. Okay, this y bar prime. in Q. And another one is A prime. A prime is the area of the other portion. Okay, so this is how you use this shear formula. Okay. If you have a rectangular cross section, you can substitute this Q and this T, and it will become this one. All right. So the maximum one which occurs in the middle, you can find it as 1.5 V over A, right? Okay, so the thing here is about this shear formula. Actually, it's a kind of average, okay, and that's, I mean, it is an estimation. We use this formula to estimate, okay. How good it is, then you need to learn more, right? But generally speaking, you can see that actually this variation will be parabolic, okay. Shear stress distribution will be parabolic. But there is a problem. The problem is, as you can see here, when you have this kind of wide flange beam, which means that you have the top flange, bottom flange, and in the middle you have the web, right? Can you see that actually from the top flange, if you have the V going down like that, from the top flange, suddenly you have the sudden change of the cross section, right? What happened now? Cross-sectional thickness T, suddenly it changes from very, very large to become quite narrow at the web, right? So what happens is that if you initially it is 0 at the top, right? And then as the shear stress going down until the very bottom, from 0 the shear stress will become something around here, okay, at this point, at the bottom portion of the flange, top flange, but suddenly it jumps to this value, right, because of the web, and then it has a parabolic distribution until it reaches the top in the middle. So the tau max will occur at the neutral axis, right, at the neutral axis, okay, and then it will reduce again, and then there is a sudden jump again, and then it becomes 0, okay. So this is problematic actually, because what really happened is that at this sudden change, let me erase first this, okay. At this sudden change of thickness, from suddenly it becomes narrow, so actually there will be stress concentration. That's the first thing. Another thing is that, I mean, this shear stress, actually shear formula, should not really used at this kind of area, right? And it's not accurate, even more not, it becomes more inaccurate around this area, around this sudden change of the thickness, right? So we have these limitations on the shear formula that you need to acknowledge. The first one is that not on the cross sections that are short or flat, okay. What I mean by that is that we go back to the previous slide, okay. If it is like this, and it looks fine, okay. I mean, depending on what is the ratio of B over H. For instance, if you have like this is fine, okay, and this neutral axis. But if you have the cross section which is like this, and this is neutral axis, it will be more inaccurate when you use this formula, okay, this shear formula, when you have this kind of flat cross section, okay. This is number 2. Number 1 is fine. I mean, they have this ratio B over H, but generally speaking, we try to avoid of having this kind of cross section. Otherwise, the shear formula will become more and more inaccurate, right? That's the first thing. Not on cross sections that are short or flat, the limitation, the first limitation. Second limitation, okay, it is not at points of sudden cross-sectional change. Okay, the example is the one that we just discussed, this junction from top flange to the this junction. Okay, I mean the rest is fine, the rest of the points are fine, the rest of the area is fine. It's just at this junction, don't rely on this formula. Okay, you can use the formula, but don't rely on the results of this formula at this junction. Okay, and not at a joint on an inclined boundary. You can find the example of this inclined boundary in the textbook. I leave that for you as a homework. Okay, remember actually you have this 7.2 when you use this formula, tau equals to VQ over IT. Again, it is an estimation. All right, you have to be careful, look at the limitations. Again, try not to use the but most of the time will be slender beam, right? So it's fine, but be careful while using this, especially when you graduated or you come across a problem and then you thought about this formula, you thought that you can use this formula. Be careful on that, because it's not just straightforward. I mean, there are limitations that we discussed. Okay, if you test and then you got very different results, then actually you should not use this formula. Okay, and we have this example 1. So I'm not going to go into the details of example 1. I just discussed very quickly. This is a wide flange beam. Okay, top flange, bottom flange. I'm not sure what happened with the mouse, and the web in between, right? And subjected to the 80 kilonewton shear force. And the question asks to plot the shear stress distribution, I think across the cross-sectional area, right? And then first thing first, find the neutral axis, the same like the one in chapter 6. Okay, look at that again. And then if you want to find the shear stress at point B prime here, for instance this point, okay, so you have to find this Q, right? Y bar prime A prime, Y bar prime A prime, and then look at this on how actually it's calculated, and then you can use the formula. Okay, and the T, the cross-sectional thickness, which is this, right? Because it's on this point B prime is in the top flange, right? So the thickness, the cross-sectional thickness is 0.3 meter, right? What else? And then of course the maximum will occur at C. Okay, if you use C, you will definitely get the maximum one. Okay, and then you can take the top area or the bottom area to find the Q, right? And then you can plot, and then you can see this, the same shape like the one that we have seen before, especially at this junction. Suddenly you have the sudden change, right? And then 7.1, we'll go to the tutorial. Please check the videos for 7.1 and 7.2 as well. Okay, 7.10 and 7.17 looks like this. This is slightly different because it is unsymmetrical about the neutral axis, right? You can see that actually the top flange is 200, the thickness of top flange is 200 millimeter, while the width of the bottom flange is W, which is not the same. It's smaller than 200 millimeter, right? Then same 7.18, and then that's the end of chapter 7. Okay, so please look at the tutorial questions and good luck. Assalamualaikum.